Hello friends, today let's look at the adaptive Huffman coding algorithm. In this video, we are going to focus on as to how a binary tree is created in this algorithm. In the next part of the video, that is part 2, we'll see as to how that binary tree is used for actual encoding and decoding of the given input. Okay, now let's look at the motivation behind the adaptive Huffman coding algorithm. The normal Huffman coding algorithm requires the knowledge of the input data in advance to find out the frequency of occurrence of each symbol. If you remember from the previous video, we had used a frequency table to compute the binary tree, and then we used that binary tree for encoding the input symbols. So, for obtaining that frequency table, we require the knowledge of the input data in advance. Now, this knowledge of input data would not be available in advance for live streaming data like live videos, audios, etc. In such cases, the adaptive Huffman coding algorithm is very useful. Okay, now let's look at the algorithm. In this algorithm, the binary tree that we are going to create must satisfy the sibling property. So what is the sibling property? This property states that each node except the root node has a sibling. If you observe this particular tree which satisfies the sibling property, and if I call this as node n0, if I call this node n1, then n2, n3, n4 and so on and so forth until this node as node n8, then you can observe that each node except the root node has a sibling. N1 and N2 are siblings of each other, then N3 and N4 are siblings of each other, and so on. The second condition of the sibling property is that the nodes can be listed in order of non-increasing weight with each node adjacent to its siblings. So, for this particular tree, if I list the nodes starting from node N0, then N1, N2. So basically, I am listing the nodes from top to bottom and from right to left. So N0, N1, N2, N3, N4. This would be N5, N6, N7 and node N8. So N0, N1, N2, N3, N4, N5, N6, N7, N8. If the nodes are listed in this particular order, then weight for node N0 is 5, weight for node N1 is 3, then weight for node N2 is 2, and so on and so forth until weight of node N8 which is 0. Weight for node N8 is 0. Now the nodes are listed in non-increasing weight order, and in this particular listing, each node is placed such that it is adjacent to its sibling. So this particular tree satisfies the sibling property. Now let's take a closer look at this tree. If we look at any node, then you can observe that it has got W part to it and N part to it. The N part denotes the node number and W denotes the weight. Now the weight at any node is basically equal to the frequency of the input symbol that the node is representing. So, if we look at this particular node which represents symbol V, the weight at this particular node is 1, which states that the frequency of symbol V in the given input is 1. Now, the N part denotes the node number. For the node which represents symbol V, the node number is 2. For the node which represents symbol NYT, node number is 1. Specifically, node numbers are assigned in such a way that a node with higher weight will have higher node number, and parent node will always have higher node number than its children. Also note that weight of parent node is equal to sum of weights of its two child nodes. Now if you remember, this was the case for original Huffman coding algorithm as well. So weight of this node is 1, which is equal to 0 plus 1. 0 is the weight for node NYT and 1 is the weight for node V. The weight for this node is 2, which is equal to weight of this node, which is 1, and weight of node, which represents symbol D. So very similar to the original Huffman coding algorithm, weight of parent node is equal to sum of weights of its two child nodes. Please note that these two rules are enforced to make sure that the created binary tree satisfies the sibling property. The first rule is a node with higher weight should have higher node number, and the second rule is parent node should always have higher node number than its children. Now if you observe this particular tree, specifically if we observe this node and this node, note that the node number for this node is 6 and node number for this node is 5. So ideally the weight for this node should be higher than this node. That is not the case. The weight for this node is 1, which is less than 2. Therefore, sibling tree property is violated in this case. A node with higher weight should always have higher node number. I hope the sibling tree property is clear now. I will be explaining and illustrating this property as we advance in this video. Now let's try to build the binary tree which would be used in this algorithm. The tree is constructed using following rules. Every tree contains a root node and a NYT node. The NYT node stands for not yet transmitted node. Note that this NYT node is kind of a special node. The purpose of NYT node would be more clear as we advance in this video. So the initial state of the tree would be this state where the root node and NYT node would be same. The weight of that node would be 0. And this n, how can we find this n? So if we know that there are n number of unique symbols that are going to appear in the input, then this n is initialized to 2n plus 1. So if we know that our live data stream is going to contain the characters or input symbols defined over the alphabet set A to Z, which is of 26 length, then this n would be 2 into 26 plus 1, that is 51. Taking another example, if we know that the input symbols are going to be taken from only 4 unique symbols, let's say A, B, C, D, then this n is 4 and therefore capital N would be initialized to 2n plus 1, which is 9. So this value of capital N denotes the total number of possible nodes in the constructed binary tree. In this case, I have initialized n to 9 by knowing that there are only 4 number of unique symbols that are going to appear, and therefore the maximum number of nodes possible is 9. Let's continue with constructing the tree. So the second rule states that when a character is read in from a file, the tree is first checked to see if it contains that character. If the character is not there, then this rule is applied, and if the character already exists in the tree, then this particular rule is applied. So let's say our first input character is character A. Obviously the character won't be present in the tree, so the first rule is applied. The first rule says that NYT node spawns into 2 new nodes. So this NYT node spawns into 2 nodes. Let's say this node 1, this node 2. The node to its right is a new node containing the character, and the new left node is the new NYT node. So the right node is node A, right? And the node to the left, that is this node, is the new NYT node. So this would be NYT node. Now the root node would no longer be NYT node. So this is not NYT node. And lastly, we need to update the weights for all nodes in the parent chain. So firstly, we need to update the weight of this node and this node. The weight of node which represents symbol A would be 1 because the frequency of character A is 1 at this point of time. The weight of NYT node would always be 0. Then the N for this node is 7 and N for this node is 8. So this node's ordering is 7 and this node's ordering is 8. Note that this ordering, which is denoted by N, increases from left to right and it increases from bottom to top. So at this point of time, we have created two nodes with NYT node as N is equal to 7, weight is equal to 0. Then A node with N is equal to 8, W is equal to 1. Now as we have discussed in the previous slide, the weight for the parent node should be sum of weights of its two child nodes. So this weight of 0 would now be updated to 0 plus 1, which is 1. So this weight would be updated to 1. Overall, after reading the first input character A, this tree would be modified to this particular tree. So the initial state of the tree was this state. We read character A and the tree is modified to this particular state. The ordering of the nodes, which is denoted by N, increases from left to right and it increases from bottom to top, right? Now let's say that the next input character is also A. Then in that case, what would happen is this particular rule will come into play, which says that if the character is already in the tree, you simply update the weight of that particular tree node. In this case, we need to update the weight of node with value as A. So this weight will be updated to plus 1. So total weight would be 2, right? Now, once we update this node, we also need to update the weights which are present in the parent chain for this particular node, right? In this case, there is only the root node which is present in the parent chain. Its weight would be updated to 2 plus 0, right? So 2 plus 0 is 2. So new weight for root node will be 2. Overall, the tree state would be modified to this state after reading this particular input. Let's continue with the input sequence. Let's say that the next input character is character R. The character R is not present in the tree already. So what we do is, we spawn this NYT node into two nodes, right? So this node would be first node, this node would be second node. Then the left node would be marked as new NYT node with weight as 0, right? The previous NYT node has N is equal to 7. So for this NYT node, N would be 5. And for this new node, N would be 6. The value for the right node would be R, right? Because the new character seen is R. The weight would be updated to 1 because R is seen for the first time. And previous NYT node would no longer be the NYT node. So I am erasing this. Now at this stage, we have created two new nodes with their W and N values updated. Now what we need to do is, because we have updated the weight for this new node, we need to update the weights for all the nodes in the parent chain. In the parent chain of this new node, there are two nodes. The node with W as 0 and root node, right? So the parent chain will be this chain. So we first update weight for this node. The weight would be updated to 1. Then we update the weight for root node. The weight would be updated to 1 plus 2, that is 3. So at this point, our tree update is complete for 3 input characters AAR. And the modified tree basically looks like this tree. Node R is inserted here. New NYT node is the left node of node R. Then weights for the parent chain of node R are correctly updated, right? Okay, now let's say that our next input character is character D. The character D is not present in the tree. Therefore, we spawn the old NYT node into two nodes. So two nodes are created from this NYT node. The left node will be marked as new NYT node. This node will no longer be NYT node. Then weight for this node would be 0 and n would be updated to 3, right? Because the n for the previous NYT node was 5. So the n for new NYT node would be 3 and n for the right new node would be 4. So this n would be 4. The value for this node would be D because the next input character is D. We also need to update the weight for the node D, which would be 1 because the frequency of character D is 1 in the given input sequence. Once we are done with creating these two new nodes, what we need to do is we need to update the weights of the nodes in the parent chain. The parent chain now consists of 3 nodes, right? This is first node, second node and third node. So the weight for this node will be updated to 1. So new weight would be 1. Now we update the weight for this particular node. The weight would be updated to 2. And finally the last node in the parent chain is root node. Its weight would be updated to 2 plus 2, that is 4. So the modified binary tree after reading 4 input characters AARD would be this particular tree. Okay, let's continue with the input sequence. Let's say that our next input character is character V. Now because the character V is not present in the tree already, what we do is we create 2 nodes out of this NYT node. So we create 2 nodes. The left node would be the new NYT node. Its weight would be 0 and n would be 1 for new NYT node. Now the right node would be node V, so its value would be V. Then its weight would be 1 because the frequency of character V is 1. N for node V would be 2, right? At this point, creation of 2 new nodes is complete. Now we need to update the weights of the nodes which are present in the parent chain. Parent chain now consists of 4 nodes. This node, then this particular node, then this node and finally the root node. Okay, let's update the weights of these nodes. So weight of this particular node would be updated to 0 plus 1, that is 1. So new weight would be 1. Now we need to update the weight of this particular node. The weight of this node would be updated to 1 plus 1, that is 2, right? So new weight would be 2. Now I need you to focus on these 2 nodes, this node and this node. For this particular node, its order is 5 and its weight is 2. And for this particular node, its order is 6 and its weight is 1. Now if you remember, while discussing the sibling tree property, what we have discussed is a node with higher weight should have a higher node number. So this particular condition is being violated when we are updating the weight to 2 for n is equal to 5, because a node with higher weight, so this is the node with higher weight, should have higher node number. So this should have higher node number, right? So what we can do is we can simply swap this node with this node, right? And after swapping is complete, then we can update the weight. So basically what is happening is when we are updating the weight of this node to 2, we are violating the rule that a node with higher weight should have higher node number. Therefore, we need to swap these 2 nodes, right? So the precise rule is that when the node is not the highest order node in its weight class, before updating the weight to 2, its weight was 1. Therefore, the weight class for this node would be 1. So all the nodes which have weight as 1 would be in the weight class of weight as 1. Now, when the node is not the highest order node in its weight class, what we need to do is we need to swap this particular node so that it fulfills the sibling property. So how do we decide as to which node we need to swap the original node with? To do that, before we update the weight, what we do is we search the tree for all nodes of equal weight and swap the soon to be updated value with the highest ordered node of equal weight. So before updating the weight of this node, its weight is 1. We search this particular tree for all nodes which have weight as 1. So I'll call this as, say, node n0, this as node n1, then this as n2, n3 and n4. So there are 5 nodes which have weight of 1. Out of these 5 nodes, which is the node which has highest order? Order is denoted by n. The highest order node would be node with value as r, right? Because n is 6, which is highest in the weight class of weight as 1. Therefore, what we do is we swap n0 with n1 without swapping the node numbers. So after swapping node n0 with node n1, the modified tree would look like this particular tree. Note that we have swapped these two nodes, but we haven't swapped their numbers. So n is still 5 for the node in this particular position, and n is still 6 for node in this particular position. Now we are safe to update the weight for this particular node. The weight would be updated to 1 plus 1. 1 plus 1, right? So the updated tree would look like this tree. The weight is now 2 for this particular node. Now the next node in the parent chain is this particular node. Its weight is 2. Now before updating the weight for this particular node, what we do is we search the tree for all nodes which have weight as 2. So those nodes would be, let's say this as n0, then this would be node n1 which has weight of 2, then this would be node n2 which again has got weight of 2. So there are total 3 nodes in the weight class of weight as 2. Now what we do is we choose the node with the highest order in this particular weight class. That node would be node n1 which has got order of 8, which is the highest order in this particular weight class. Now to maintain the sibling property, we again need to swap n0 with n1. So we need to swap this node and this node while keeping the n same at that particular position. So after swapping these two nodes, the modified tree would look like this tree. Now this node is the highest order node in its weight class. So we are safe to update the weight for this particular node. The weight would be updated to 1 plus 2, that is 3, right? So the modified tree after updating the weight would look like this. Now the last node remaining in the parent chain is the root node. Root node is always going to be the highest order node in the binary tree. Therefore, we don't need to do anything while updating the weight for root node. So we simply update the weight for root node to 2 plus 3, that is 5, right? So the updated tree would look like this tree. Now at this point of time, we have read 5 input characters and the tree update for these 5 input characters is complete. This particular tree maintains the sibling property. The sibling property of the tree is maintained by using this particular rule. The rule is, when the node is not the highest order node in its weight class, we search the complete binary tree for all nodes which have got the same weight or which are in the same weight class. Then what we do is we swap the soon to be updated value with the highest order node of equal weight, and finally we update the weight. So this particular rule is very important for maintaining the sibling tree property. I hope that the tree update rules are clear now. In the next video on the adaptive Huffman coding algorithm, we are going to use these tree update rules along with the encoding and decoding schemes for actually encoding and decoding the input sequence. For similar questions, you can visit our website www.ideserve.co.in. For our new video updates, please subscribe to our YouTube channel. Thank you and cheers.